Imagine a world, not the familiar blue and green marble we know, but a swirling, incandescent sphere, barely recognizable as Earth. This was our planet approximately 4.5 billion years ago, during a period of immense cosmic violence and creative chaos, known as the Hadean Eon. The solar system was still a vast, dusty construction site, a turbulent maelstrom where planets were not yet fully formed, but rather coalescing from countless smaller fragments. It was a time of relentless bombardment, where leftover debris from the sun's birth still hurtled through space, smashing into nascent planetary bodies with terrifying regularity. This early Earth, or proto-Earth as scientists refer to it, was a world adrift, a primal furnace simmering with untold energies, a place utterly inhospitable by any modern standard, yet brimming with the raw potential for everything that would follow. The landscape, if one could even call it that, was an apocalyptic vision. There were no oceans of liquid water, no continents rising majestically from the waves, no breathable atmosphere. Instead, Proto-Earth was a vast, molten ocean of glowing orange-red rock, stretching for thousands of kilometers in every direction. The surface was a churning, roiling expanse, resembling a disturbed pot of boiling stew on an unimaginable scale. Only, instead of water, it was silicate rock, iron, and nickel, all superheated to temperatures far exceeding 1,000 degrees Celsius. Immense plumes of vaporized rock and intensely hot gases would erupt from fissures, momentarily obscuring the already dim, star-dusted cosmic background. This infernal panorama was not static. It was a dynamic, terrifying crucible, where the very elements of our planet were still sorting themselves out, differentiating into layers, with denser materials sinking towards the core and lighter ones remaining closer to the surface. This early proto-Earth was also a planet without a stable axis, a condition that would make any concept of predictable seasons or even a consistent day-night cycle utterly meaningless. Picture a child spinning top, not rotating smoothly, but wobbling wildly, its axis of rotation gyrating erratically through space. This was proto-Earth, tumbling and lurching through its orbit around the young sun. One moment, a vast region might be bathed in the faint, distant sunlight for an extended period, only to be plunged into prolonged darkness as the planet tilted away, its orientation constantly shifting. Such instability meant that any nascent processes attempting to establish themselves on the surface, such as the initial cooling of a thin crust, would be immediately disrupted by radical temperature swings and gravitational stresses. The very concept of up or down would have been a fickle, fleeting notion on such a volatile, unsettled sphere. Compounding this axial instability was Proto-Earth's astonishing rate of rotation. Our world today completes a full rotation in approximately 24 hours, giving us our familiar day. But Proto-Earth spun at an incredible, dizzying speed, completing a rotation in as little as 2 to 6 hours. Imagine the forces at play on such a rapidly rotating body. The centrifugal force would have been immense, potentially distorting the planet into a slightly oblate spheroid, flattened at the poles and bulging at the equator, far more pronounced than it is today. If you could have stood on its surface, an impossible feat, the distant stars would have streaked across the sky in a blinding blur, and the horizon itself would have seemed to rush past with terrifying velocity. This rapid spin contributed to the constant churning of the molten interior, driving convection currents that would eventually play a crucial role in forming Earth's magnetic field, but at this stage, primarily added to the overall instability and dynamism of the young planet. This wasn't just a world of internal turmoil. It was also a cosmic shooting gallery. The early solar system was still teeming with planetesimals, rocky and metallic bodies ranging in size from small asteroids to objects hundreds of kilometers across, essentially the leftover building blocks of planets. Proto-Earth was a massive gravitational target, constantly bombarded by these remnants. These impacts were not mere meteor showers. They were cataclysmic events, each one capable of unleashing energy equivalent to billions of atomic bombs. When a large planetesimal, perhaps the size of a small moon, slammed into Proto-Earth, the consequences were devastating. Molten rock would be splashed thousands of kilometers into space, forming ephemeral plumes that would rain back down as incandescent droplets. The impact would generate colossal seismic waves rippling through the molten body and release unimaginable amounts of heat, further delaying any chance of a stable crust forming. Each collision would add mass, reshape the planet's nascent topography, and contribute to its overall chaotic state. The atmosphere, if it can be called that, was a suffocating, superheated blanket of vaporized rock, carbon dioxide, sulfur compounds, and other volcanic gases, far denser and more corrosive than anything known on Earth today. It would have been opaque, trapping heat and preventing any view of the cosmos from the surface. The sky would not have been blue or even hazy grey, but rather a perpetual glowing orange or red, illuminated by the fiery surface below and the constant flashes of impacts above. This was a world still very much under construction, a violent workshop where the materials were being hammered, melted, and reformed into something new. There was no true stable surface, no predictable rhythm, no settled state. It was a planet in perpetual motion, a world on the brink, awaiting a defining event that would irrevocably alter its destiny and set the stage for its long, complex journey towards becoming the cradle of life. This proto-Earth, spinning wildly, glowing fiercely, and relentlessly battered, was preparing for the most significant collision in its history. The early solar system, a realm still largely undefined, continued its violent, chaotic dance. Proto-Earth, a rapidly spinning incandescent sphere, was not alone in its fiery solitude. For countless millennia, it had been growing, sweeping up cosmic dust and planetesimals. But a far greater encounter was destined to occur, an event that would irrevocably alter its very being. This pivotal moment arrived approximately 4.51 billion years ago, when another significant celestial body, a nascent world we now call Theia, embarked on its fateful trajectory towards our nascent planet. Theia, a protoplanet roughly the size of Mars, to give you a sense of scale, Mars has a diameter of about 6,979 kilometers, had been gravitationally interacting with Proto-Earth for an unknown duration. It was not a sudden, unexpected ambush, but rather a slow, inevitable convergence orchestrated by the complex gravitational forces within the burgeoning solar system. Imagine two colossal cosmic billiards balls, each glowing with internal heat, drawn towards each other with an unstoppable, accelerating momentum. As Theia drew closer, its gravitational pull would have begun to deform Proto-Earth, stretching and kneading its already molten surface, causing unimaginable upheavals and tides in its liquid rock ocean. The approaching protoplanet itself would have appeared as an increasingly immense, fiery orb in Proto-Earth's sky, growing larger and more menacing with each passing hour, a harbinger of the cataclysm to come. The collision itself was not a head-on impact, which would likely have resulted in the complete annihilation of both bodies, leaving behind only a larger, more chaotic molten mass. Instead, scientific models suggest it was an oblique, glancing blow, a high-speed sideswipe that occurred at an estimated velocity of around 15 to 20 kilometers per second. To put that into perspective, that's roughly $54,000 to 72,000 kilometers per hour, many times faster than any projectile created on Earth. The sheer kinetic energy involved was staggering, an amount almost incomprehensible. It was equivalent to trillions of megatons of TNT exploding simultaneously, dwarfing any natural event humanity has ever witnessed. The moment of contact would have been marked by an instantaneous, blinding flash of light, visible across vast distances of the early solar system, followed by an explosion of unimaginable power. The crust and mantle of both Proto-Earth and Theia, already superheated, were instantly vaporized and melted. Shockwaves, traveling faster than sound through solid rock, would have ripped through the colliding bodies, transforming their internal structures in mere seconds. The initial impact would have gouged out a tremendous amount of material from Proto-Earth's side, while Theia itself would have been largely disintegrated, its core potentially merging with Proto-Earth's, and its mantle fragmented into billions of superheated pieces. This was not merely a collision, it was a cosmic demolition and reconstruction. The force of the impact was so immense that it ejected a vast plume of molten rock, vaporized silicates, essentially vaporized stone, and superheated metal fragments into space. This material, flung outward with incredible velocity, initially formed a glowing, expanding cloud around the newly reformed, even larger, and now even more incandescent Proto-Earth. Think of it as a monstrous cosmic splash, where the water is molten rock and the spray consists of vaporized minerals. The temperatures generated during this event were extreme, potentially reaching tens of thousands of degrees Celsius, hot enough to turn solid rock into a gaseous plasma. The immediate aftermath was a sight of unparalleled chaos and fiery beauty. Proto-Earth, now scarred and swollen, would have been completely remelted, transforming into an even deeper, more turbulent ocean of incandescent magma, perhaps hundreds or even thousands of kilometers deep. Its entire surface would have glowed with an intensity that would eclipse any star in the night sky. The sheer energy imparted by the collision would have further accelerated its rotation, potentially shortening its day even more from its already rapid spin. Above this inferno, the ejected debris, a swirling maelstrom of molten droplets and vaporized rock, began to spread out, caught in Earth's powerful gravitational field, eventually forming a vast luminous ring of incandescent material orbiting the nascent planet. This ring was unlike anything seen today. It wasn't a delicate band of ice and dust like Saturn's rings, but a dense, turbulent torrent of molten rock, metal, and gas, constantly colliding and interacting. Each fragment, from microscopic dust grains to multi-kilometer-sized chunks, was a miniature furnace, radiating intense heat into the vacuum of space. The material would have glowed a fierce orange, red, and white, making the newly reshaped Earth appear as if it had acquired a halo of fire. The gravitational forces within this ring, coupled with the immense heat, prevented the material from immediately dispersing, instead forcing it into a stable, albeit incredibly dynamic orbit. This cataclysmic event, the collision of Proto-Earth and Theia, was not just a destructive force, it was a creative one. It was the ultimate cosmic recycling program. The material ejected into orbit was not lost. It was the raw, superheated building blocks for Earth's future companion. The impact reset Earth's clock, in a sense, wiping away much of its previous geological history and beginning a new chapter defined by this monumental encounter. The very composition of the debris ejected, a mixture of proto-Earth's mantle and Theia's disintegrated body, would ultimately determine the Moon's unique geological fingerprint, a composition that scientists have meticulously studied for decades to confirm this colossal Genesis event. Without this violent collision, our world, and perhaps even the very possibility of life as we know it, would be fundamentally different. Theia's fury was a moment of destruction that paved the way for creation, leaving behind a profound and lasting legacy. The colossal impact of Theia had left Proto-Earth irrevocably changed, a glowing, rapidly spinning orb, almost entirely remelted. But the drama did not end there. Surrounding this renewed, incandescent world was a spectacle of cosmic proportions, a vast, swirling ring of incandescent debris born from the violence of the collision. Imagine, if you can, a band of fire stretching hundreds of thousands of kilometers across the primordial void, a luminous halo around a searing planet. This was no ordinary ring of dust and ice like those around Saturn. This was a superheated, turbulent maelstrom of vaporized rock, molten metal droplets, and larger fragments, all moving at incredible orbital velocities, locked in a gravitational dance around their parent body. The temperature within this ring was staggering, reaching thousands of degrees Celsius, hot enough to vaporize most known materials. This extreme heat was a direct consequence of the impact itself, which had injected immense kinetic energy into the ejected material, transforming it into a high-energy plasma and molten spray. Particles of iron, silicon, magnesium, and oxygen, the fundamental building blocks of rocky planets, were not merely solid fragments, but often existed as superheated gas, condensing into tiny liquid droplets or microscopic solid grains, only to be vaporized again by subsequent collisions. This environment was akin to a perpetual planetary-scale forge, radiating an immense amount of light and heat into the surrounding darkness. Within this fiery torus, chaos reigned, yet it was a chaos with an inherent order. The inner parts of the ring, closer to Proto-Earth, orbited faster, while the outer regions moved more slowly, creating constant shear forces. This differential motion, combined with the sheer density of the material, meant that collisions were incessant. Billions upon billions of particles, from microscopic dust grains to boulders the size of small mountains, slammed into each other, exchanging momentum, shattering, remelting, and sometimes beginning to stick. It was a cosmic demolition derby, but one where the fragments were slowly, inexorably beginning to build something new. The process of building began with the simplest interactions. Initially, electrostatic forces, similar to the static cling that makes clothes stick together, allowed the tiniest dust particles to gently coalesce. As these small clumps grew, their individual gravitational pull, however weak, started to become significant. Picture these growing aggregations as cosmic snowflakes, slowly gathering more and more material. Over time, these small aggregations would attract others, beginning a process known as accretion. This wasn't always a gentle affair. Many collisions were still energetic enough to shatter the nascent clumps, but statistically, the tendency was towards growth. Larger bodies possess stronger gravitational fields, allowing them to sweep up more material more effectively, leading to a runaway growth where the biggest fragments grew fastest. The dense concentration of material in the ring, unlike the much sparser asteroid belt or even current planetary rings, was crucial for the rapid formation of the Moon. With so much available raw material packed into a relatively confined space, the chances for particles to interact and merge were incredibly high. Imagine a crowded highway during rush hour, but instead of cars, you have billions of rocks, all trying to occupy the same space and constantly bumping into each other. This high density meant that the Moon didn't take millions of years to form. Instead, it coalesced with astonishing speed. Scientific models suggest that from the time the debris ring was established, the entire process of gathering this material into a single, cohesive body might have taken only a few centuries, perhaps as little as 100 years, or at most, a few thousand. For a celestial body, this is a blink of an eye. As gravity relentlessly pulled these fragments together, a single, dominant body began to emerge within the ring. This proto-moon, as it accumulated mass, was itself a molten sphere. Every impact, every particle that joined its growing bulk, released kinetic energy upon collision. This energy was instantly converted into heat, maintaining the proto-moon in a superheated liquid state. It would have glowed with its own incandescent light, a smaller, fiery sibling to the still molten proto-Earth. It was a world of liquid rock, churning and roiling under the constant bombardment of leftover debris from the very ring it was forming from. While the proto-moon grew, its increasing gravitational dominance also began to clear the surrounding ring. It acted like a cosmic vacuum cleaner, sweeping up the remaining fragments, either incorporating them into its own mass or flinging them out of orbit. Over time, the once vast, luminous ring would have thinned, becoming less spectacular as its material was either consumed by the growing Moon or scattered by its gravitational influence. The Moon, now a substantial body, would have continued to grow until most of the available material in its orbital vicinity was either part of its mass or had been gravitationally nudged away. At this early stage, the Moon was a much closer companion to Earth than it is today. Its orbit was likely only a fraction of its current distance, perhaps as close as 20,000 ciphers to 30,000 kilometers, compared to the present-day average of 384,000 kilometers. From the surface of the early Earth, the Moon would have appeared as an enormous dominant sphere, filling a significant portion of the sky. Its gravitational pull on Earth would have been tremendously powerful, creating colossal tides in the nascent oceans that were just beginning to condense from the steamy atmosphere. This close proximity also meant the Moon orbited Earth much faster, perhaps completing a circuit in just a few hours. As the bombardment subsided and the proto-moon achieved its approximate final mass, it began the long process of cooling. This cooling happened from the outside in. The surface, exposed to the frigid vacuum of space, would have been the first to solidify, forming a thin, fragile crust over a vast global ocean of molten rock, known as a magma ocean. This magma ocean would have been hundreds of kilometers deep, slowly solidifying over millions of years. Within this deep molten interior, a fundamental process called differentiation began. Denser elements, like iron and nickel, slowly sank towards the center, forming the Moon's core. Lighter elements, like silicates, floated upwards, eventually crystallizing to form the lunar mantle and crust. This process of differentiation and the cooling of the magma ocean left indelible marks on the Moon, marks that scientists can still read today. Analysis of lunar rocks brought back by the Apollo missions, particularly those rich in a unique geochemical signature known as creep, potassium, rare earth elements, phosphorus, provide strong evidence for this global magma ocean phase. These elements, incompatible with common rock-forming minerals, would have become concentrated in the last remaining liquid fractions as the magma ocean solidified, eventually forming distinct rock types. The Moon's heavily cratered surface, much of which formed during the late heavy bombardment era that followed its initial cooling, further tells a story of a violent past, but one where the primary formation was complete. So, from a cataclysmic collision that vaporized entire worlds, a new body emerged with astonishing speed. The chaotic, fiery ring, a temporary monument to destruction, quickly coalesced under the relentless pull of gravity into a single molten sphere. This sphere, initially a close glowing companion to Earth, then slowly cooled and solidified, beginning its long journey to become the familiar, pockmarked orb we gaze upon today. This rapid genesis was not merely an interesting astrophysical event. It was the birth of an indispensable partner, one whose very existence would fundamentally shape the destiny of Earth itself. The catastrophic impact of Theia had left Proto-Earth irrevocably changed, a molten, incandescent sphere reborn from the collision. Yet, in the immediate aftermath, a far more profound transformation was beginning, one that would sculpt our planet into the habitable world we know today. The newly formed Moon, initially a colossal, glowing orb of molten rock and vapor, orbited incredibly close, its immense presence dominating the early Earth sky. This proximity was not merely a visual spectacle. It was the engine of a gravitational dance that would fundamentally stabilize a chaotic world. Before the Moon's arrival, Proto-Earth was a truly wild and unpredictable place. Imagine a gigantic, unbalanced top spinning furiously on a table. Its axis, the imaginary line around which it rotates, would wobble erratically, constantly shifting its orientation. This was the plight of our nascent planet. Without the steadying influence of a large, nearby celestial body, Proto-Earth's rotational axis was prone to significant, unpredictable changes. The gravitational tugs from the distant Sun and other nascent planets, though individually weak, could easily nudge and shift Earth's axis, causing it to precess or wobble like a dying gyroscope through vast angles. This meant that any given region on the surface could, over relatively short geological timescales, swing from being directly beneath the scorching equatorial sun to experiencing extended periods of frigid polar darkness. There were no stable seasons, no predictable climate patterns, just a relentless, chaotic flux that would have made the emergence of any complex, stable environment incredibly difficult, if not impossible. Then came the Moon. Its substantial mass, even in its earliest molten form, exerted a powerful and continuous gravitational pull on Earth. This pull acted as a colossal cosmic anchor, dampening Earth's wild, chaotic wobble. Think of it as the gravitational equivalent of adding a heavy, perfectly balanced flywheel to that wobbling top. The Moon's gravity interacted with the Earth's equatorial bulge, the slight outward swell around the equator caused by its rapid rotation. This interaction created a torque, a twisting force that worked to stabilize Earth's axial tilt. Over millions of years, this constant, gentle gravitational persuasion guided Earth's axis into a relatively stable orientation, settling it at approximately 23.5 degrees relative to its orbital plane around the Sun. This precise angle is not arbitrary. It is the reason we experience seasons. It means that as Earth orbits the Sun, different hemispheres are tilted towards or away from our star at different times of the year, leading to the familiar cycle of spring, summer, autumn, and winter. Without the moon's stabilizing influence, Earth's axial tilt might have swung wildly from 0 degrees, meaning no seasons, constant equatorial heat, and perpetual twilight at the poles, to nearly 90 degrees, resulting in extreme devastating seasonal changes where each pole would alternately bake under direct sunlight for half a year and then plunge into complete darkness for the other half. The moon, therefore, didn't just appear. It brought order to chaos, laying the foundational stone for a predictable climate. But the moon's influence extended beyond merely stabilizing Earth's tilt. Its close proximity to the rapidly spinning proto-Earth initiated another profound transformation, the slowing of our planet's rotation. In the immediate aftermath of the Theia impact, Earth was spinning at an astonishing rate, completing a full rotation in perhaps as little as 2 to 6 hours. This meant that a day was incredibly short, a blur of motion where the sun would streak across the sky, rising and setting multiple times in what we now consider a single waking period. The centrifugal forces generated by such rapid rotation would have been immense, constantly trying to flatten the planet and fling material outwards. The moon, initially orbiting at a mere 25,000 kilometers from Earth's surface, roughly 1/15 of its current distance, exerted an enormous gravitational pull. This pull was so strong that it deformed Earth itself, creating massive tidal bulges, not just in any nascent oceans, but in the molten rock and metal of the entire planet. Imagine a colossal molten blob being stretched and squeezed by an even larger nearby gravitational force. As Earth spun rapidly beneath these immense tidal bulges, a fascinating interaction occurred. The bulges, being gravitationally attracted to the moon, were constantly trying to align themselves with the moon's position. However, Earth's rapid rotation dragged these bulges slightly ahead of the direct line between the Earth and the moon. This slight misalignment created a powerful braking force, a phenomenon known as tidal braking. The moon's gravity was constantly tugging back on the leading tidal bulge, trying to pull it into alignment. This continuous tug-of-war acted like a giant invisible brake pad, relentlessly sapping rotational energy from Earth. Picture the Earth spinning, dragging its molten tidal bulges, while the nearby moon constantly pulls on those bulges, creating friction and slowing the planet's spin. This wasn't a sudden jolt, but a gradual, persistent process that unfolded over billions of years. The rotational energy lost by Earth was not simply dissipated, it was transferred to the moon, causing it to slowly accelerate in its orbit and spiral outwards, away from Earth, at a rate of about 3.8 centimeters per year. This process continues even today, albeit at a much slower pace. The consequences of this tidal braking were monumental. Over vast stretches of geological time, Earth's day gradually lengthened. From those initial frenetic 2 to 6 hour rotations, the planet slowed to its familiar 24-hour cycle. This lengthening of the day had profound implications for Earth's environment. With a longer day, periods of sunlight and darkness became more extended, allowing for more gradual heating and cooling of the surface. This reduced extreme temperature swings, creating more stable conditions for geological processes and, eventually, for the emergence and evolution of life. Longer nights allowed for more significant cooling, which was crucial for the solidification of Earth's molten crust and the eventual condensation of water vapor to form oceans. The reduction in centrifugal forces also contributed to a more stable planetary structure. Thus, the moon, born from a cataclysmic collision, immediately began its work as Earth's indispensable architect. It didn't just orbit our world, it actively reshaped it, taming its wild spin and stabilizing its tilt. These two fundamental changes transformed Proto-Earth from a volatile, unpredictable inferno into a world capable of fostering complex geological processes and, ultimately, life. The Moon became and remains our planet's steadfast anchor, its gravitational presence a silent, continuous force that underpins the very rhythm of our world. The Moon, our silent sentinel, did not merely establish Earth's initial stability. Its gravitational embrace has continued to sculpt our world, orchestrating rhythms that have profoundly influenced the emergence and evolution of life itself. The story of Earth's habitability is inextricably linked to the ongoing dance between our planet and its colossal companion, a cosmic ballet that has unfolded over billions of years. Imagine the early Earth, its days now stretched to a more manageable length, its axial tilt stabilized. Yet, the Moon, still much closer than it is today, exerted a gravitational pull far more intense than what we experience. This immense force generated truly colossal tides. While today our oceans might rise and fall by a few meters, or perhaps a dozen in extreme locations, in those ancient times, the liquid oceans and even the planet's solid crust would have experienced bulges hundreds of meters high. Picture towering walls of water sweeping across nascent continents, inundating vast coastal plains, and then retreating to expose immense stretches of seabed. These were not the gentle lapping waves we know, but a relentless, powerful pulse, a daily reshaping of the planet's surface with an energy almost beyond comprehension. These supertides were a geological force of immense magnitude. They ceaselessly scoured coastlines, eroding nascent land masses with a power that dwarfs modern processes. They carved out immense bays, deep inlets, and intricate estuaries. Sediment, churned and transported by these powerful currents, would have been deposited in rhythmic layers, forming ancient tidal flats and deltas that, over billions of years, solidified into distinct geological formations. Scientists today can sometimes identify these tidal rhythmites in ancient rock strata, offering a tangible echo of those primordial moon-driven forces. These rhythmites, like geological clockworks, preserve the signature of the Moon's early, rapid recession and the corresponding slowing of Earth's rotation, providing invaluable data points about the deep past. The very geography of our early planet was being etched by the Moon's gravitational hand, creating a dynamic interface between land and sea that would prove crucial for life. It is within these constantly shifting intertidal zones that some of life's most pivotal steps may have been taken. These areas, periodically submerged and then exposed, are rich in nutrients, constantly mixed by the ebb and flow of the tides. They become natural laboratories where conditions fluctuate dramatically, challenging any organisms that call them home. Early microbial mats, simple biofilms, and the first single-celled organisms would have found both refuge and relentless pressure in these environments. The relentless exposure to air, sunlight, varying salinity, and temperature swings would have selected for adaptability, driving evolutionary innovation. These zones were the literal edge of the known world for early life, pushing the boundaries of what was possible for survival. Consider the wet-dry cycles hypothesis, a compelling idea in the scientific quest to understand the origin of life, or abiogenesis, the process by which life arises from non-living matter. This theory suggests that the repeated cycles of wetting and drying in these early tidal pools could have been crucial for the formation of complex organic molecules. Imagine a pool of water laden with simple organic precursors, amino acids, nucleotides, the basic building blocks of life. As the tide receded and the sun beat down, the water would evaporate, concentrating these molecules and potentially facilitating their polymerization. When molecules like amino acids dry out, they are more likely to link together to form proteins. Nucleotides can form RNA or DNA, the carriers of genetic information. Then, with the return of the high tide, these newly formed, more complex molecules would be rehydrated, dissolved, and perhaps undergo further reactions. This rhythmic, moon-driven dance of concentration and dilution, of synthesis and interaction, provided the perfect crucible for the earliest forms of self-replicating molecules to emerge. A chemical symphony played out on the shores of a nascent world, guided by the moon's gravitational baton. Beyond the initial spark of life, these intertidal zones served as an unparalleled training ground for life's momentous transition from water to land. For billions of years, aquatic organisms were confined to the oceans, protected by their watery medium. But the fluctuating conditions of the tidal flats offered a gradual yet persistent challenge. Organisms that could tolerate periods of desiccation, the loss of water, or develop primitive methods of breathing air, or even move short distances on exposed surfaces, would gain a significant advantage. This selective pressure, applied daily by the moon's gravitational pull, would have slowly but surely favored the development of stronger fins that could eventually become weight-bearing limbs, the evolution of more robust protective coverings to prevent water loss, and the adaptation of respiratory systems capable of extracting oxygen from the atmosphere rather than dissolved in water. It's a long, arduous journey spanning hundreds of millions of years, but the moon provided the consistent, rhythmic push that drove species to leave their aquatic cradle and begin the colonization of the continents, forever changing the face of Earth's biosphere. Yet the moon's gift to life extends far beyond the dynamic shores. Let's revisit its role in stabilizing Earth's axial tilt. Our planet currently spins at an angle of approximately 23.5 degrees relative to its orbit around the Sun. This tilt is the fundamental reason we experience seasons. Without it, the Sun would always be directly overhead at the equator, and the poles would remain in perpetual twilight, leading to a much more uniform and less dynamic climate across the globe. However, if the moon were not present, Earth's axial tilt would not be stable. It would wobble chaotically, potentially swinging from 0 degrees, no tilt, no seasons, to as much as 80 degrees, extreme tilt, with poles sometimes pointing directly at the Sun, over timescales of millions of years. This chaotic behavior is due to the gravitational tugs from other planets, particularly Jupiter, which would otherwise destabilize Earth's spin axis. Imagine a world where, over geological epochs, the poles could suddenly become tropical, or the equator could plunge into an ice age. Such radical shifts in axial tilt would lead to unimaginably extreme and unpredictable climate swings. Entire continents could experience rapid transitions from scorching deserts to frozen wastelands, or from lush rainforest to arid steppes, all within a few million years, a blink of an eye in evolutionary terms. This constant, unpredictable environmental upheaval would make the sustained evolution of complex life incredibly difficult. Ecosystems would collapse before they could fully adapt, and biodiversity would likely be severely stunted, perhaps even preventing the rise of complex multicellular organisms altogether. The Moon, by acting as a gravitational anchor, has maintained Earth's tilt within a relatively narrow and predictable range for billions of years, providing a climate stability that is rare among planets. This stability has been absolutely paramount for the long-term development of complex life and the astonishing biodiversity we see today. Predictable seasons, driven by a stable axial tilt, allowed ecosystems to evolve and adapt to consistent environmental rhythms. Organisms could specialize, develop intricate life cycles tied to seasonal changes, and rely on consistent patterns for reproduction, migration, and food availability. From the annual bloom of phytoplankton in the oceans, to the migratory patterns of birds and the hibernation cycles of mammals, life on Earth has evolved to synchronize with these lunar-stabilized seasonal cues. Without this predictability, the intricate web of life, with its countless interdependencies, might never have reached such complexity or resilience. The Moon ensures that while Earth's climate does change over vast geological timescales, these changes are generally gradual enough to allow life to adapt, rather than being subjected to sudden, catastrophic shifts that would reset the evolutionary clock. The Moon's gravitational presence also subtly influences global atmospheric and oceanic circulation patterns. Stable seasonal temperature gradients drive predictable wind patterns and ocean currents, which in turn distribute heat and moisture across the planet. This contributes to the long-term stability of major climate zones, from the tropics to the temperate regions and the poles. The consistent flow of ocean currents, like the Gulf Stream, which helps moderate Europe's climate, relies on these stable planetary conditions. Without the Moon's stabilizing hand, the chaotic tilt of Earth would lead to wildly fluctuating circulation patterns, making long-term climate modeling, and indeed, long-term biological evolution, a far more challenging and perhaps impossible endeavor. The Moon, therefore, plays a direct role in maintaining the very conditions that allow for a diverse array of biomes and habitats across our world. In essence, the Moon is far more than just a beautiful object in our night sky. It is a fundamental architect of Earth's habitability. It provided the dynamic stage of the intertidal zones for life's earliest acts, and then served as the unwavering conductor, setting the rhythm of seasons and climate for billions of years. Life on Earth has not just existed alongside the Moon. It has co-evolved with it, shaped by its tides and sustained by its stabilizing influence, from the first single-celled organisms in a tidal pool to the complex ecosystems of today. The Moon's presence has been a constant, gentle, yet incredibly powerful force, guiding the trajectory of our planet's biological history. It is the silent partner in the grand story of life, the anchor that keeps our world on an even keel, allowing the vibrant symphony of existence to play on, an ongoing testament to a violent birth that yielded an eternal companion. From its violent birth in a maelstrom of cosmic debris to its quiet, steadfast presence in our night sky, the Moon has been Earth's unwavering companion, a silent witness to billions of years of planetary evolution. It is far more than just a pretty orb. It is the fundamental anchor that has shaped our world, guiding its spin, stabilizing its tilt, and orchestrating the very rhythms that allowed life to flourish. The story of its formation, a tale of catastrophic collision, is a reminder of the dynamic and often brutal forces that forged our familiar cosmos. Today, the Moon continues its slow, majestic retreat, moving approximately 3.8 centimeters further from Earth each year. This gradual separation is a direct consequence of the same tidal forces that have been at play since its formation. As Earth's rotation drags the tidal bulges slightly ahead of the Moon's direct line of sight, the Moon exerts a gravitational pull on these bulges. This pull acts like a brake on Earth's spin, slowing our planet down, while simultaneously transferring angular momentum to the Moon, causing it to accelerate slightly in its orbit, and thus drift further away. This ongoing dance of celestial mechanics ensures that the moon's influence, while subtly diminishing, remains a constant in our lives, notably through the tides that ebb and flow along our coastlines, shaping ecosystems and human endeavors alike. Without the moon, our days would be shorter, our climate more chaotic, and our oceans far less dynamic. Yet, despite the compelling evidence supporting the giant impact hypothesis for the moon's formation, this grand narrative is not without its intriguing mysteries and ongoing scientific debates. One of the most persistent and fascinating puzzles revolves around the precise composition of Theia, the Mars-sized protoplanet believed to have struck proto-Earth. Lunar rocks, brought back by the Apollo missions and later robotic probes, have revealed a striking similarity in isotopic composition to Earth rocks, particularly for elements like oxygen, titanium, and tungsten. Isotopes are different forms of the same element, varying only in the number of neutrons in their nucleus. Since different planetary bodies are expected to have slightly different isotopic signatures, the near-identical nature of Earth and Moon isotopes presents a challenge. If Theia was a distinct body, formed in a different part of the early solar nebula, one might expect its material, which contributed significantly to the Moon, to bear a unique isotopic fingerprint. Several scientific explanations have emerged to reconcile this apparent discrepancy, each painting a slightly different picture of the cataclysm. One leading hypothesis suggests that the impact was so incredibly energetic and violent that it thoroughly mixed the material from both proto-Earth and Theia before the Moon coalesced. Imagine a cosmic blender operating on an unimaginable scale, churning and vaporizing rock and metal into a uniform, superheated cloud. In this scenario, the resulting Moon would naturally inherit an averaged isotopic signature, closely resembling Earth's. Another theory posits that Theia, by sheer cosmic coincidence, might have formed in the same general region of the solar nebula as proto-Earth, and therefore inherently possessed a very similar isotopic composition from the outset. While less elegant, it remains a possibility within the vast randomness of early planetary formation. A more radical and recently proposed model, known as the synestia hypothesis, offers yet another solution. A synestia is a rapidly spinning donut-shaped vaporized body that forms when two planetary-sized objects collide at high energy and angular momentum. In this scenario, the impact between proto-Earth and Theia would have created a massive, hot, rotating cloud of vaporized rock, metal, and gas, hundreds of times larger than Earth. Within this turbulent, superheated structure, the Moon would have condensed and solidified from the inside out, gradually growing within the synestia's atmosphere before the rest of the vaporized material collapsed back onto Earth. This process, by its very nature, would ensure an exceptionally thorough mixing of materials from both impactors, leading to the observed isotopic similarities. Scientists continue to refine these models through sophisticated computer simulations, pushing the boundaries of our understanding of these extreme cosmic events. Each new lunar sample, each detailed analysis, brings us closer to unraveling the full truth of our Moon's origin. The pursuit of these answers drives ongoing and future lunar exploration. Missions like NASA's Artemis program are not merely about returning humans to the Moon. They are scientific endeavors aimed at establishing a sustained human presence and, critically, at expanding our knowledge of lunar geology and its formation. Future astronauts and robotic probes will delve into unexplored regions, seeking out older rock samples that could provide a clearer picture of the Moon's initial formation and differentiation. The search for water ice, impermanently shadowed craters at the lunar poles, exemplified by missions like the Viper rover, is not only crucial for future human outposts, but also holds clues about the delivery of volatiles to the early Earth-Moon system. Understanding the distribution and origin of water on the Moon could shed light on whether Theia itself carried significant amounts of water, or if it was delivered later by comets and asteroids. Commercial Lunar Payload Services, or CLPS, also represent a new era, allowing private companies to deliver scientific instruments and technology demonstrations to the lunar surface, accelerating our rate of discovery. Each landing, each sample collected, helps to piece together the cosmic puzzle, adding detail to the broad strokes of the giant impact hypothesis. Beyond the scientific intrigue, the Moon holds an indelible place in the human story. For millennia, it has been our constant companion in the night sky, a source of wonder, inspiration, and mystery. Ancient civilizations tracked its phases to create calendars, guiding agricultural practices and seasonal rituals. Poets have immortalized its serene glow. Lovers have gazed upon its distant beauty, and storytellers have woven intricate myths around its enigmatic presence. It has been a symbol of constancy, of change, and of the profound unknown. For humanity, the Moon is more than just a celestial body. It is a profound testament to our own origins. Its very existence reminds us that our familiar, habitable Earth is not a static entity, but the product of an incredibly violent, dynamic past. It is a world born from a cataclysmic collision, forged in fire and chaos, yet ultimately destined to become a cradle for life. The Moon serves as a constant reminder of the incredible forces at play in the cosmos, forces that can both destroy and create, shaping destinies on a planetary scale. It underscores the fragility and preciousness of our blue planet, while also inspiring us to look beyond, to explore, and to understand the universe that birthed us. Our eternal companion continues its slow spiral outward, a quiet sentinel in the vastness of space. It stands as a monumental marker of a pivotal moment in Earth's history, a silent guardian that has stabilized our world, sculpted our oceans, and perhaps even nudged life onto its evolutionary path. As we continue to gaze upon its familiar face, whether through telescopes or with the naked eye, we are looking at a fundamental piece of ourselves, a testament to a grand cosmic drama that played out billions of years ago, forever intertwining the fates of Earth and its magnificent Moon. It is a story still being written, with each new discovery adding another layer to the epic saga of our home world and its celestial